is lesson 2, investigation 1, coordinates and vectors. We're going to do questions 1 through 3. Our goal is to learn about the relationship between the coordinates of the terminal point of the position vector and its components, and to be able to write what's called parametric equations. And we'll learn what parametric equations are a little bit later. In our think about, let me delete this from earlier because I don't want it here. Suppose a rectangular coordinate system is placed on a nautical map so that Milwaukee National Marina is located at the origin with a positive x-axis pointing east and a positive y-axis pointing north. So what we're saying here is we now are going to put our vectors on a coordinate plane. The speedboat leaves the marina in a direction of 30 degrees and proceeds at 16 knots. Let's draw that. Here's what this looks like. Label this as your x, y coordinate plane, 30 degrees, and traveling at 16 knots. How could the distance and direction traveled after 1/4 hour be represented by a vector on a coordinate system, after 1/2 hour and after 1 hour? Well, think about it like this. If we're traveling at 16 knots, and we go for the knots being nautical miles per hour, and we travel for a quarter of an hour, that's 1/4 of 16. That vector would look like this. About 1/4 of that entire length, and it would be 4 nautical miles long. If we did this for a 1/2 hour, that would be about half of that vector. And that would be labeled 8 nautical miles. They both would have a 30-degree angle. And lastly, if we did this for the full 1 hour, at 16 knots, we would have traveled 16 nautical miles. So part B. What are the coordinates of this boat's position after a 1/4 hour, after a 1/2 hour, and after 1 hour? 1/4 hour. Use your skills from last week. You have a horizontal and a vertical component. The horizontal is x, the vertical is y. This point has the ordered pair x comma y. We found x last week by taking the magnitude times the cosine of the angle. So x is 4 cosine 30 degrees. Y is sine. So 4 times the sine of 30 degrees. 4 times the cosine is 3.46. 4 times the sine is 2. So what is the location of the boat after 1/4 hour in a coordinate plane? The boat is located at 3.46 nautical miles east, 2 nautical miles north. Now we can do the same thing for a 1/2 hour, the same thing for 1 hour, and calculate those. But I'm not going to go into every one of those single problems. But here's what we did in general. If I know the distance traveled, then, for example, 16, then this is 16 cosine 30 degrees, comma 16 sine 30 degrees. This would be 8 cosine 30 degrees, 8 sine 30 degrees. So in general, given a coordinate plane of xy and a vector of theta with a fixed fixed magnitude, fixed magnitude of r, then the point xy is just r cosine theta, r sine theta. And that's literally taking the work from last week and applying it to a coordinate system. So let's use these concepts to try to develop what's called parametric equations. So let's start out with just a little bit more practice. Now you have these on your handout, so you can use them. Unfortunately, it's a little bit difficult for me to use them here, so I am going to delete a couple of them. My ruler doesn't work either, so I'm going to just leave that. We want to sketch a vector and find the coordinates on a coordinate plane. The vector in A1 has a magnitude of 4, an angle of 145 degrees. I've already marked 145 degrees. I need to measure 4 units out. Now I'm going to have to eyeball it. You can be a little bit more specific. 1, 2, 3, 4, that's 4. 1, 2, 3, 4, yep. Now you can follow your arc and get a pretty close estimate of where 4 would be. For me, 4 is going to be right about there. So there's my vector of 4 units, 145 degrees. I need to find xy. X is going to be 4 cosine 145. Y is 4 sine 145. Therefore, my coordinates for xy come out to be 3.28, comma 2.29. Now, whether you are in class or at home watching this, well, if you're at home, pause this and answer the next 2 questions, part 2 and part 3. In class here, I will pause it and have you complete those 2 problems, and we will check our answer. Just a point of clarification, part 1, it should be a negative 3.28, not a positive problem. Number 2, help me out, class. I think if we go 3 to 40, 240 degrees is going to be done in this direction. 3 units long. I want to find xy. X comes out to be negative, what was that? Yeah, negative 1.5. Comma, negative 2.6. Checking your work on this one. 315, 5 centimeters. Remove that. Down about there. X comma y. X comes out to be 3.54. Comma y. And negative 3.54. So how can you find coordinates xy? The terminal point of a vector, if you know only its magnitude and its direction? Well, it's going to be r cosine theta, or r cosine theta, comma, r sine theta. Exactly what we wrote on the previous slide. So now number 2. And I need need to get rid of a few things here because it's not quite working out using the technology as I had planned. So now we're going to start to develop even a little bit more of a parametric situation, or a parametric equation. So suppose the speedboat, and to think about, traveled at a direction of 130 degrees rather than 30. Sketch the path of the boat traveling at a speed of 16 knots on a coordinate system and identify its position at a half hour, 1 hour, and 2 hours. Let's start with 1 hour. If he's traveling at 16 knots, 1 hour would be a total of 16 nautical miles. So here's your 130 degrees. Here's our vector. We're going to say right here, at this particular point, is 16 nautical miles. Therefore, if he travels for a half hour, class, spell it loud so that those listening online can hear. What's half of 16? That would be right about there. And we'll call that 8 nautical miles. And lastly, class, 2 hours at 16 knots, total distance is 32. That's going to be 16, right about there. And so that represents 32 nautical miles. What are the vector components of each? In other words, what are x and y? If I take the first vector, that is my x, here's my y. X is always magnitude times the cosine, y is always magnitude times the sine. Well, let's think about this. That was 1 times 16. Let me change that around. That was 16 times 1 times the cosine of 130. 16 times 1 times the sine of 130. Which comes out to be a negative 10.28. Comma 12.26. When you said that the second vector, or this half and a half of 1 hour vector, was 8 nautical miles long, you got the 8 by taking 1/2 times 16, or 16 times 1/2. Therefore, this ordered pair is 16 times 1/2 times the cosine of 130, and 16 times 1/2 times the sine of 130, which is a negative 5.14, comma 6.13. Notice anything else? And lastly, the coordinates of this longer vector, the 2 hour vector, those coordinates were 16 times 2 times the cosine of 130, 16 times 2 times the sine of 130. And we can come up with those values if we really need to. Here's what's happening in general. You are finding a distance. Think back. You are finding a distance by taking rate times time. And that's what your distance formula is. Your distance formula is rate times time. Here's your distance. Again, distance was rate times time. So our equations for x and y, x is rate times time times the cosine of our direction, and y is rate times time times the sine of our direction or angle. Where rate times time is just distance, or what we've also called magnitude. So here's what we are working on. We just created two parametric equations. In parametric equations for linear motion models, walking, aircraft, flying, if you want to put that in there. I know my language use isn't consistent. Boats, cars, hiking, or anything with rate times time, where we are traveling at some specific rate. Therefore, if v is some vector, magnitude r, angle theta, then a set of parametric equations that model linear motion is r times t times the cosine of theta, r times t times the sine of theta. All parametric means is that we have included a third variable of time that tells us where we are along the vector. So let me just look back. Not only do we have an x and a y variable telling our location, but there's a t variable telling us how far into the walk we are. You can skip that. And so our last problem. Now consider a standard coordinate system that can be used to model linear motion of an aircraft. Suppose a commercial jet leaves New York City and flies at a direction of 190 degrees towards the west coast at 60 miles per hour. Assume that this direction and average speed take into account the force exerted by headwinds. Model this situation by placing New York City at the origin of the coordinate system and sketch the aircraft's path. Then we will find rules for the rectangular coordinates of the position of the aircraft t hours into the flight. Assuming no deviation from the course, then find the coordinates of the aircraft's position after a quarter hours and 3.2 hours. What are the coordinates of the aircraft's position when it has flown 2,000 miles? So we'll also take a look at that. So starting out, let's model this situation. Here's our coordinate plane, x, y. The center, New York City, 190 degrees. And we are traveling at 600 miles per hour. That's our rate. Therefore, any point on here, x comma y, has the coordinates of 600 times the amount of time in air times the cosine of 190, comma, 600 times t times the sine of 190 degrees. We found the rules. Now find the coordinates after a quarter hour. We'll plug 0.25 in there. So after 1/4 hour, I'm just gonna write this a little bit differently to show that we can. 600 times 0.25 times the cosine of 190. Y is 600 times 0.25 times the sine of 190 degrees. And those values, or that ordered pair, is a negative 147.72, comma, a negative 26.05. Now if we do this after 3.2 hours, x equals 600 times 3.2 times cosine of 190. Y is 600 times 3.2 times the sine of 190, giving us values of a negative 1,890.83, comma, negative 333.4. On part C, it asks, what are the coordinates of the aircraft's position when it